Hi everyone, I finished my setup of 30 cooling systems per min and I will go through how I did it in this video. As you can see, the resources are being used now, when compared to my last video on my small setup of the same cooling systems. This took me some time, as all of my setup is running on overflow method, and there were some problems with water, but here we are, finally done. And the platform above is the place where I showed the small setup in my previous video. So, let's get right into it. I have multiple stages like how I explained in my previous video and I will go through in a similar way. You will be seeing a lot of refineries. Step 1 uses alternate recipe called sloppy alumina. This takes 200 bauxite and 200 water to make 240 alumina solution. In total, I am bringing in 600 bauxite. So 600 divided by 200 needed by recipe is 3. So I have 3 refineries here. And I am feeding the water required by each by a separate pipe. Since each requires 200, I'm bringing in 3 pipes of water. In total, I am outputting 720 alumina solution from step 1. Please find the exact inputs and outputs on the screen for easier information. For my next phase I will be making petroleum coke. I will let you know in a second why. Using the alumina solution from step 1, I am going to make aluminium scrap. And for this recipe we need petroleum coke. So, let's move on to step 2. Step 2 uses the alternate recipe called heavy oil residue, which takes in crude oil and outputs heavy oil residue and polymer resin as a byproduct. I am bringing in 300 crude oil and this recipe takes 30. So 300 divided by 30 is 10. We need 10 refineries in total. And this recipe outputs 40. So we get 400 heavy oil residue and 200 polymer resin. So these are the 10 refineries which are making heavy oil residue. As for the resin, let's talk about it soon. Step 3 involved recipe called petroleum coke, which takes in heavy oil residue and makes petroleum coke. And, since the output of step 2 and input of step 3 are the same, I am directly feeding the heavy oil residue to this refinery, to reduce the mess. Since we have 10 refineries and bring in 400 residue, in total we make 120 into 10 equaling 1200 petroleum coke per minute. Now we have used one of the outputs from step 2 which is heavy oil residue. Now for the other output which is polymer resin, we have the step 4 now. So to recap, from step 2 which is heavy oil residue, we give 300 crude oil and get 400 heavy oil residue and 200 polymer resin. We have used 400 heavy oil residue in step 3. Now for the 200 polymer we go into step 4. Step 4 is residual rubber. Here we send the polymer resin as input and water to get rubber as an output. So, I am bringing a separate line of water for this recipe as well. As for the step 4 maths, since we bring in 200 polymer resin, and this recipe takes 40, 200 divided by 40 is 5. So we need 5 refineries and similarly 200 water as well. And we output 100 rubber in total. This side is where we input the resin and here we merge all the rubber and send it to the last step to make cooling systems. We will discuss about that at a later part of this video. As you can see here, the standard recipe is taking rubber as an input, and since we decided for 30 cooling systems, we need a total of 60 rubber in this entire setup. Since we are making 100 rubber and 60 is needed in this setup, I am sending the remaining 40 to the resource sink. So this step 4 is for residual rubber, where we take 200 polymer resin and 200 water to make 100 rubber. Now, both the outputs of step 2, which are heavy oil residue and polymer resin, is used in step 3 and step 4 respectively. Now, to step 5. In step 5 I use alternate recipe called electrode aluminium scrap. This uses alumina solution from step 1 and petroleum coke from step 3 to make aluminium scrap and water. I I have also overclocked all 3 refineries to 133.33%. This is to take the 240 alumina solution from previous step and directly feed it here, instead of collecting them and sending them, which is more complex. As for the petroleum coke, one refinery needs 80, so in total we need 240 petroleum coke for this setup. As each refinery outputs 120 coke from step 3, I am sending 2 refineries worth of petroleum coke, which is 240 to step 5, which is making aluminium scrap. As for all the other 8 refineries, where the other 960 petroleum coke is being sent to a resource sink as of now. My plan is to make a steel factory in the future with this. As for the step 5 maths, one refinery outputs 400 aluminium scrap and we have 3, so 400 times 3 is 1,200 aluminium scraps per minute. Now, let's go to step 6 for using the aluminium scraps. Step 6 involves alternate recipe called pure aluminium ingots, which takes the aluminium scraps to make aluminium ingots. As you can see, I am bringing in 3 separate lines of 400 aluminium scraps from the 3 refineries from previous step. Now for the step 6 maths. Since we get 400 per line, 400 divided by 60 needed by the recipe, we get 6.66 smelters. As you can see here, every setup has one of the smelters underclocked to 66.66%. This is the second set of 6.66 smelters, and that is the third and final set. Now, for the maths again, please check the revised one here for the on-screen maths, and to calculate the ingots, 6.66 into 30 equals 200 aluminium ingots per line. And, since we have 3 lines, we get a total of 200 into 3 equaling 600 aluminium ingots per minute. I am then merging all the 600 aluminium ingots and sending it to step 8 to make Alclad ALuminium sheet. We are still in step 6. This is because Alclad ALuminium sheets also requires copper ingot. So in step 7, we will make aluminium ingots. This Alclad ALuminium is step 8 and we will discuss it later. For step 7, I am bringing in 300 copper from a different biome. For step 7, I am using alternate recipe called pure copper ingot, which takes copper ore and water to make copper ingots. For the water, here, if you remember, we are getting water as a byproduct from step 5 where we make aluminium scraps. This is the water I am talking about. If you remember, we are getting 140 into 3 equaling 420 water as an input from this step 5. And this pure ingot recipe takes in 10 per refinery. So for step 7 maths, we bring in 300 copper Oregon. So 300 divided by 15 equals 20 refineries. And for water, 20 into 10 equals 200 water requires for this step. As for the outputs, which are copper ingots, 20 refineries into 37.5 ingots equals 750 copper ingots per minute. I have merged, and you can see here, there is a steady stream of copper ingots flowing to the next 2 steps. This is step 7. I have a small setup which I am going to call 7.5 and show you guys what I did. If you remember, we have 420 water from step 4. And we utilized only 200 of it in the step 7 to make copper ingots. So we still have 220 water remaining. In step 7.5, I am using alternate recipe called pure quartz crystal. Here I am utilizing the extra quartz which I am using in other setups to make quartz crystal. And I have 6 refineries set up for the same. Now, just the water calculations, as we have 220 water remaining. And this recipe takes 37.5 per minute. So 220 minus 37.5 into 5 equals 32.5 still remaining. And as you can see, I have underclocked the 6th refinery to take in exactly 32.5 water. Now for the step 7.5 full maths, we input 396 raw quartz and 220 water to make 52.5 quartz crystal of 5 refineries equaling 262.5 from 5 of them and 45.5 from last, totaling 308 quartz crystal per minute. I am then merging them and storing it in my storage facility for my future use. So step 7.5 is done. Now, we finally go into step 8. The recipe is Alclad ALuminium sheets. It takes both aluminium ingots from step 6 and copper ingots from step 7 to make Alclad ALuminium sheets. As for the step 8 maths, since we get 600 aluminium ingots, and this recipe takes 30, 600 divided by 30 equals 20. So we need 20 assemblers in total. And I have 10 assemblers in a row, and I have 2 rows of assemblers in this step. So in total, this step takes in 600 aluminium ingots and 200 copper ingots to make 600 Alclad ALuminium sheets. To check on copper, we are making 750 copper ingots from previous step. And since this step takes 200, we still have 550 copper ingots left. These ingots will be used in the next step, which we will discuss. So, in total, as I mentioned, we are making 600 Alclad ALuminium sheets per minute. And let me show you what I am doing with it. I have merged all of them and sending the sheets to the step 10, which is not the next step. And we still have some remaining. I am storing all the remaining ones as they can be used for Mark V belts. This is the step 10 and I am showing now. Here you can see, we need these Alclad ALuminium sheets to make heat sink. So, I am using a smart splitter to overflow on the right and store them while sending the required via the middle. Before moving on the next step, we now have the 600 Alclad ALuminium sheets from step 8. But in order to make heat sinks, we also need copper sheets, as the standard recipe heat sink takes Alclad ALuminium sheets and copper sheets to make heat sink. And as I mentioned at the start, I have planned to make 30 cooling systems per minute and the recipe takes 12 per minute. In total we have 5 blenders, so we need 60 heat sinks. And the heat sink recipe outputs 7.5 per minute. So, 60 divided by 7.5 equals 8. So in total, we need 8 assemblers to make heat sinks. Since we decided we need 8 assemblers, we need 8 into 37.5 equaling 300 Alclad ALuminium sheets. Now, as you know, we are getting 600 Alclad ALuminium sheets from step 8, and step 10, which is heat sinks, requires only 300 Alclad ALuminium sheets. We are sending 300 to this step and 300 to the storage. Now for the step 9, where we are making copper sheets required in step 10. Step 9 uses normal copper sheets recipe, which takes in copper ingots and outputs copper sheets. If you remember, in step 7, where we were making copper ingots, we are currently outputting 750 copper ingots and step 8 takes 200 ingots. So remaining we have 550 copper ingots. This is the step 8 where aluminium sheets are being made. So, for the step 9 maths, we need to know how many copper sheets are required in step 10. Since the recipe takes 22.5 and we have 8 assemblers, 22.5 into 8 equals 180 copper sheets. Our copper sheets recipe outputs 10 copper sheets per minute. So 180 divided by 10 is 18. So we need 18 constructors in total. Here I have 9 constructors in a line and I have 2 lines of constructors. Some of them are yellow, because they already have full copper sheets and are slowly sending it to the step 10. Now for the step 9 maths. This recipe takes 20 copper ingots to make 10 copper sheets. And since we are getting 550 copper ingots from previous step 7, 500 minus 20 ingots required into 18 assemblers, which is 190 ingots still remaining. As for the remaining ingots, I am currently sending them to a resource sink. In future I might use them for other setups if needed. I couldn't let it stay in the system, as the refineries from step 7 needs to constantly use the excess water from aluminium scrap recipe. So, this is it for the step 9. Just a reminder, we take 360 copper ingots and make 180 copper sheets from this step 9. Now, to step 10, where I am making heat sinks. Here I am using the standard recipe called heat sinks, which takes Alclad ALuminium sheets and copper sheets to make heat sinks. For the step 10 maths, the recipe needs 37.5 sheets and we have 8 assemblers, so 37.5 times 8 is equal to 300 Alclad ALuminium sheets, and the recipe needs 22.5 copper sheets, so 22.5 times 8 is equal to 180 copper sheets. And for the output, 7.5 into 8 equals 60 heat sinks per minute. I am then merging everything and sending it to step 10 finally. Now to the step 10, where we are making cooling system. Now for step 10, I am using the standard recipe, cooling system. This takes in heat sinks, rubber, water and nitrogen gas to make cooling system. I have set up 5 blenders for the same. So, for the step 10 maths, this recipe takes 12 heat sinks and 12 rubber, and we have 5 blenders, so 12 times 5 equals 60. So this requires 60 heat sinks and 60 rubber. And it also requires 30 water. So 30 into 5 equals 150 water for this setup. As you can see, I am bringing it in a single pipe. Now for the nitrogen gas, it requires 150. So 150 times 5 equals 750 nitrogen gas per minute. For this I am bringing in 2 pipes of nitrogen gas to this setup. This Mark I pipe is bringing in 300 nitrogen gas and the other Mark II pipe is bringing in 450, so in total I am bringing in 750 required in this setup. Since each blender requires 150 nitrogen gas, the Mark II pipe will feed 3 blenders, while the Mark I pipe will feed 2 of them. I have also connected both these pipes, so that there won't be any shortage and any problem since it is a gas. Now, all 4 inputs are coming in properly to these 5 blenders and a total of 30 cooling systems is being outputted per minute. I have merged all the blender outputs and I am sending it to storage as these are required for future Tier 8 buildings. In total, I am sending 3 resources to my storage from this setup. One is 30 cooling system which we discussed now, and second is 308 quartz crystal from step 7.5, and third is 300 Alclad ALuminium sheet from step 8. I am sending the rubber to resource sink, as I am already storing it from another setup. These are the 3 output lines to storage and a single input line for raw quartz. So, this is my setup of 30 cooling systems per minute and I am storing them for future use. Once enough is stored they are going to resource sink. Currently I am getting 1.2 million points per minute at its peak and in general a little less than that. So these cooling systems will also join soon, but it's going to take some time. In the spare time, I will build something else in my playthrough. Before the cooling systems, I produced 30 radio control unit, and I am just setting the board for my easier access in the future. Now with these radio control units and cooling systems created, I am planning to create supercomputer. The supercomputer recipe I am using is in assembler. It is an alternate recipe called OC supercomputer. This takes 9 radio control unit and 9 cooling systems to make 3 supercomputers per minute. Since I am producing 30 of each, I am planning to use 3 assemblers to use 27 radio control unit and 27 cooling system to make 9 supercomputers per minute. I don't know if that quantity is enough or not, but let's see in the future. Let me show my storage room for a sec, as I have been storing the radio control unit and now cooling system for some time. This is my storage room which I showed you guys in my transition video. Already 1400 cooling systems has been stored, and I have 12 containers worth to store still. As you can see, after storing the 12 containers, everything goes to resource sink to get tickets. I am currently building a new 3-part storage facility, which I have explained in my other videos, and the location is near the waterfall. And here is my start of the train station, where I will build a resource sorting facility and send 40 different type of resources to the new storage facility. The radio control unit and cooling system are the last 2 resources I made, and I have already stored 12 containers worth of radio control unit. Now, it's time for the cooling systems. I am trying to get the count of radio control units stored currently in my facility, as they are being used to make blenders. In a storage container, we have 8 columns and 6 rows, so in total 48 spaces for the resources. And radio control units are stored in 50 per stack. So 50 times 48 equals 2,400 per container. And since I have 12 containers, I am storing 2,400 times 12 equaling 28,800 radio control units in total. And as for the cooling systems, it's in stack of 100, so 48 times 100 equals 4,800 per container. And if it fills up, 4,800 times 12 equals 57,600 stored here. That's it for this video, and thanks for watching, where I am showing my setup of 30 cooling system per minute. If you like this video, please consider liking and subscribing for more content like this in future. Thanks, and see you in the next video.